If you want to model a particle trapped in a static potential well, standard quantum mechanics works perfectly. You use a fixed wave function equation, like the one shown here for an electron. But there is a strict limitation baked into this mathematical framework. It assumes the total number of particles in your system is constant. An electron can move, it can change energy states, but it cannot disappear. But in an actual LED, an electron and a hole completely vanish from the material to create light. Because the particle count is changing, the fixed wave function equation breaks down mathematically. It simply has no vocabulary to describe a particle ceasing to exist. To build real quantum hardware, engineers require an upgraded mathematical framework. We need a system that natively handles the creation and destruction of particles. This equation shows the baseline physical process behind an LED. An electron combines with a hole to emit a single photon. Classically, we might describe this as an electron simply falling to a lower energy state, but the strict quantum mechanical description is much more demanding. We have to track 3 simultaneous events. An electron disappears from the conduction band, a hole disappears from the valence band, and a photon appears in the electromagnetic field. This is where second quantization comes in. It is a framework where physical processes are written directly as mathematical operator sentences. Mastering this quantum grammar is the first step to engineering modern optoelectronics, from simple displays to advanced lasers. Every language needs nouns and verbs. In second quantization, the verbs are operators. An operator adorned with a tiny cross, called a dagger, creates a particle. An operator without a dagger annihilates one. For a conduction band electron, the notation includes its specific wave vector and spin. Applying this dagger operator creates an electron precisely in that state. Now consider a semiconductor hole. In quantum mechanics, a hole is defined by an absence. This equation defines a hole creation operator. It shows that creating a hole physically means annihilating a pre-existing electron from the normally full valence band. This table summarizes our semiconductor vocabulary, providing mathematical triggers to create and annihilate conduction electrons and valence holes. The final piece of our vocabulary is the photon creation operator, a dagger. It represents a quantized excitation in the electric field, which is exactly what an emitted photon is. With the nouns and verbs established, we can now string them together to construct the interaction Hamiltonian, the master equation that governs the device. This equation is the full interaction Hamiltonian for light emission in second quantization. To understand what this mathematical phrase actually does, you have to follow the cardinal rule of quantum operator syntax. You read it right to left, matching the physical action. Starting on the right, the first action annihilates a conduction band electron. Moving left, the second action annihilates a hole, restoring the missing valence electron. Finally, the third action creates a photon in the electromagnetic field. This notation shows the initial state containing an electron and a hole. When the operator sentence executes, the system transitions to a final state where the pair is gone, and one photon is emitted. A complex multi-particle quantum event is elegantly governed by this single-ordered mathematical phrase. Writing the sentence is just the first step. Engineers use Fermi's golden rule to calculate the actual transition rate. The delta function inside the rule enforces strict energy conservation. The combined electron and hole energy must precisely match the emitted photon. This equation shows the second requirement. The crystal momentum of the electron and hole must also sum to 0, conserving momentum across the entire interaction. Direct bandgap materials like gallium arsenide are highly efficient because their electrons and holes naturally satisfy both energy and momentum conservation in a single, simple transition. Contrast that with this operator for silicon. Silicon's momentum doesn't naturally align, so the equation requires an extra operator, B dagger, to create a lattice vibration, or phonon, to balance the momentum. This makes it a lower probability, second-order process. The efficiency of a semiconductor device is directly readable from the length and complexity of its second quantized operator sentence. More operators mean lower efficiency. If an LED and a laser diode use the exact same fundamental recombination process, why do they produce such radically different types of light? The answer lies in this equation, detailing the mathematical properties of the photon creation operator when it acts on a state that already contains n photons. The probability factor breaks into 2 components, a constant 1, and a variable n. The 1 drives spontaneous emission, producing broad, incoherent LED light even in empty modes. The n drives stimulated emission. In occupied modes, n drastically enhances photon creation, producing a laser. The structural divide between simple indicator lights and the high-speed lasers powering global fiber optics is governed entirely by that single bosonic multiplier. This table demonstrates that second quantization is the universal modeling language for all modern quantum hardware. If we take the LED operator sentence and run it in reverse, annihilating a photon to create an electron and a hole, we accurately model a solar cell. By swapping in an operator to represent a bound electron-hole pair, or exciton, we define the exact emission pathway of an organic LED display. Applying the same grammatical logic to the creation and annihilation of Cooper pairs defines the frictionless behavior of superconductors. Second quantization turns invisible, probabilistic physical processes into precise, actionable mathematical actions. It provides the concrete, operational language required to move quantum mechanics out of theoretical physics and